In our first lecture, we worked with continuous time signals, where the signal is defined for every real value of t. Now we move to a fundamentally different type, discrete time signals. A discrete time signal, x of n, is defined only at integer values of n. Between these integers, the signal simply does not exist. We represent discrete time signals using stem plots, where each value appears as a dot at the top of a vertical line. This is very different from the connected curves we drew for continuous time signals. Let us look at a concrete example. Consider x of n with the following values. At n equals -3, the value is 0.5. At n equals -2, it is -2. At n equals -1, 0.5. At n equals 0, 1. At n equals 1, 2. At n equals 2, 1.5. And at n equals 3, 0.5. Each value is an isolated point. We can also write this compactly using vector notation. X of n equals the sequence 0.5, -2, 0.5, 1, 2, 1.5, 0.5, with an arrow marking the position of n equals 0. Vector notation is a convenient shorthand for discrete time signals. We list the values in order and place an arrow underneath to mark which element corresponds to n equals 0. Values to the left of the arrow correspond to -n, and values to the right correspond to +n. This compact representation will be especially useful when we perform operations like shifting and scaling, because we can track how the n equals 0 position moves. How do we obtain discrete time signals in practice? Through sampling. Given a continuous time signal x sub c of t, we sample it at regular intervals of t sub s seconds. The result is x of n equals x sub c of n times t sub s, where n is an integer. Graphically, imagine placing vertical stems at every t sub s seconds along the continuous curve and reading off the values at those points. The continuous curve between samples is discarded. The sampling period t sub s determines how finely we capture the original signal. Smaller t sub s means more samples and better representation. Now let us learn our first discrete time operation, shifting. Given x of n, we can create a delayed version y of n equals x of n minus n0, where n0 is a positive integer. This shifts the entire signal to the right by n0 positions. In vector notation, this is equivalent to shifting the n equals 0 pointer to the right. For example, given x of n equals the sequence -1, 2, 0.5, 3, 0.5, with n equals 0 at the third element, to find x of n minus 1, we shift the n equals 0 pointer one position to the right. The signal values stay the same, but they now occur one step later. We can also advance a signal by shifting it to the left. For y of n equals x of n plus n0, we shift the n equals 0 pointer to the right by n0 positions, which effectively moves the signal to the left. For x of n plus 1, the pointer shifts right by 1. For x of n plus 2, it shifts right by 2. In general, to draw x of n plus n0, shift the n equals 0 pointer to the right by n0. To draw x of n minus n0, shift the pointer to the left by n0. This convention is the same as what we learned for continuous time signals, but now we only deal with integer shifts. Let us review what we have covered. Discrete time signals are defined only at integer values of n, and we represent them using stem plots or vector notation with an n equals 0 marker. We obtain them from continuous time signals through sampling, where x of n equals x sub c of n times t sub s, and we can shift them in time. X of n minus n0 delays the signal by n0 steps, while x of n plus n0 advances it. In the next lesson, we will learn two more operations, time scaling and time reversal for discrete time signals.